Hey everybody, today we're having a look at the connection between finding the area under a curve and the primitive of a function. Remember, when you are finding the primitive, you are finding the function that you differentiated to get the derivative. So function, derivative, integration, or the primitive to get the original function. Let's look at the example on page 118, which gives a basic lead into this concept. The book gives an example of an object travelling at a constant velocity of 30 meters per second over time. For those of us who have studied motion in physics, you would know that there is a relationship between distance, velocity, that is speed, and acceleration. Now, if we graph distance against time, the gradient of the line gives us the velocity of the object. So in other words, the gradient function, that is the derivative, gives us the graph of velocity. Let's have a look at the next slide. On the left-hand side, I've copied the original graph from the textbook into GeoGebra. The graph in the textbook was in millimeters and pretty hard to figure out what was going on. On the right-hand side, I've done another graph where I've graphed distance against time. Basically, all it is doing is using this information that we're given. So, in 1 second, it's travelled 30 meters. After 2 seconds, it's travelled 60 meters, and so on. So if we go back to the original question about finding the area under the curve of the velocity graph, we can have a look here and work this out quite easily. This is the area, I'll just shade that in there, that's the area between 0 and 1 seconds. 30 high, 1 across, gives an area of 30 units. Okay, between 0 and 2, that includes this rectangle as well. So 30 times 2 gives a total of 60. And they asked the area under here, so that's 30 times 3, which is 90. Okay, so that's that part. Let's have a look at these two graphs and what they represent. The graph on the left is our velocity graph. We could write a function for it like this. We could write v equals f of t, which equals 30 meters per second. The graph on the right represents the primitive of this function. We could call it, say, capital F of t. So we could have, say, distance equals capital F of t. Now, the primitive of 30 in terms of t will be 30t. So that equals 30t plus the constant. Now, in this case, we're going to take the constant as being equal to 0. But in reality, in these calculations of area under curves, we don't have to use the constant. We can ignore it because basically what happens is the constants cancel out. Now, let's read off the distances off our distance time graph. From 0 to 1 is from 0 to 30. From 0 to 2, it goes from 0 up to 60. From 0 to 3 is from 0 up to 90. So they're equivalent to the areas underneath our curve over here. Now, if we wanted to calculate how far an object travelled from, say, 1.5 seconds to 3 seconds, we could find the difference between the two function values. That is, we could do, let's see, where are we? We could do function 3, capital F3, minus function 1.5. Now so function 3 we said was 90, which is 3 times 30, minus 1.5 times 30, and that gives us 90 minus 45, which is 45 meters. Okay, so we can find the distance between 2 points this way, which is equivalent to the area over here. Now 1.5 to 3, we could calculate out the area there to be equal to 45 as well. Now, what about finding areas under curves? We've done approximations using trapezoidal and Simpson's rules, but these are only approximations. We want exact values, so we'll use the primitive function to calculate exact areas. Let's have a look at a GeoGebra app that I found that compares approximations and using primitives to find areas under curves. And this is an introduction to the fundamental theorem of calculus. Now, looking at the screen, it's pretty busy, but let's go through all the parts. Now, over here on the left-hand side, function x equals 2x. That's the curve that we're finding the area. That's the curve that we're finding the area between the x-axis and the function line. In this particular case, I've already set it up. It's between the function x is 2x, and it's between the points 1 and 3. Now this part here, this will be a bit scary to you, but this is using a different approximation method from trapezoidal and Simpson's. It's called Riemann sums, but basically it does a very similar sort of thing. What it does, you've got the left sum as the big rectangle that goes above the function line. The right sum is the one that goes below the function line. So basically it calculates the areas of the left ones, which gives you the answer there. The right ones are these ones here, and it's the difference between, it's the average of those two that give you the area. Now, this box up here gives us the width of each strip. This little slider over here varies the number of rectangles, so we go from 1, I think you can go right up to 62, just to sort of increase the accuracy, but we're not going to be worried too much about that. Now, so that's the left-hand side of the screen. On the right-hand side of the screen over here we have the primitive function. Okay, that was little f of x. This is big F of x, which is the primitive of 2x. Primitive 2x is x squared. Now it shows the range of the calculation we were doing from 1 to 3. So down here we've just got the difference in the two functions. It's function 3 minus function 1. Function 3 is 3 squared, which is 9. Function 1 is 1 squared, which is 1. 9 take 1 is 8. So the area under the curve over here is 8 square units. Now that's what we've got over here is actually a trapezium shape, and we could have just calculated that out anyhow. But when we get to doing curves, this calculation will be essential. Now let's have a look, see what happens when how we do a calculation under a curve. I'm going to change my function value here. I'm going to change it to a nice easy one, 3x squared. Okay, we're going to have to change these things a bit. Okay, we might just change the range a bit. Okay, so we can fiddle this in. Yeah, we just can zoom in on that a bit. Now, okay, so here we have function x equals 3x squared. Basically, it's a fairly skinny parabola, and we're doing the calculation of the area under the curve between 1 and 2. Now, the approximation works out to be 7 using Riemann squares. Okay, we can adjust the number of rectangles here, but it doesn't change. Okay. Now, when we go over onto the right-hand part of our screen, we're looking at the integral. The integral of 3x squared, you should know by now, is x to the power of 3, x cubed. And by substituting f of 2 and f of 1 in there, f of 2 is 2 cubed, which is 8. F of 1 is 1 cubed, which is 1. 8 take 1 is 7. So the area under the parabola, 3x squared, between 1 and 2, is exactly 7 square units. So that leads us to the fundamental theorem of calculus. The fundamental theorem of calculus states that the area enclosed by the curve y equals f of x, the x-axis, and the lines x equals a and x equals b is given by the integral from b to a of f of x dx is f of b minus f of a, where f of x is the primitive function of fx. So just these values over here. A is the start point, b is the end point. Now, there is quite a involved proof for this in our textbook. I'm not going to go there this lesson, apart from just saying that, have a look at that. Does that look familiar there? That's a little bit of limits and first principles differentiation there, but I might do that on a separate video. We could be here for ages looking at that, so let's move on to the next slide. Now, okay, by the fundamental theorem of calculus, the integral from b to a of function x dx equals f of b minus f of a, where f of x is the primitive function of fx. And just to refresh our memory, they've given the primitive formula for the primitive function. Okay, so, and they say, putting these pieces of information together, we can find areas under simple curves. Now, the book gives us some examples, and look how simple this is. We've got to evaluate the area under the curve of 2x plus 1 over the intervals 3 to 4. Now, all we have to do, and just see how they set it out here. We've got this sort of curly F-type symbol for the integral. The start point's at the bottom, the end point's at the top. The function is in brackets. After that is dx equals, and then square braces. Then we integrate the function. So the integral of 2x is x squared. The integral of 1 is x. Notice there's no constant. And close the square braces off, and at the top we put the end point, at the bottom we put the start point. And so then on the next line we just the first part is substitution of the endpoint. So we're replacing x with 4, so 4 squared plus 4, then minus the start point, which is 3, so it's 3 squared plus 3. Do the calculation, answer is 8. Now, as I said before, if there was a plus c there and a plus c there, they would cancel themselves out, because plus c minus c gives you nothing. So that's why we don't use a constant here. Down the bottom we have the graph that represents this area. Okay, next example. We have the integral of 0 to 5 of 3x squared. That's a bit like the other example I did from GeoGebra. Okay, once again we have the integral sign from 0 to 5, 3x squared dx equals square braces. The integral of 3x squared is x cubed. The start and finish points are 0 and 5. We substitute those points into the primitive. So 5 to the power of 3 minus 0 to the power of 3 is 125. And once again, we have a graph representing that situation. Oh, by the way, you could copy these down into your book as we go along. Pause your video and copy them in. Okay, next graph. Integral from 0 to 2 of minus 3x squared dx. Now minus 3x squared dx you probably will recognize as being a concave down type parabola. Okay, let's see what happens in this case. The integral of minus 3x squared is minus x to the power of 3. And the range is between 0 and 2. Substituting these into our function, minus 2 cubed minus 0 cubed gives you minus 8. Now we get a negative answer for area. So we don't normally have negative values for in area, but in this case, anything below the line, below the x-axis I should say, is negative area. Anything above the x-axis is positive area. Later on we're going to have to be careful when we're finding areas under curves that traverse the x-axis, because the negative part cancels out part of the positive part. Okay, next question. We've got the integral from minus 1 to 1 of x cubed dx. Now, so the integral of x cubed is x to the power of 4 over 4, using our formula, and it's between minus 1 and 1. Now, x to the power of 4 is symmetrical, and we've got minus 1 and plus 1. Once we've done the calculations, we end up with an answer of 0. And so what's happened there, we've got a positive answer on this side, a negative answer on this side. They're both equal, so they cancel each other out. So that's why we get 0 for our answer. Now that's pretty well it for the fundamental theorem of calculus. You could then go on and do the questions out of the textbook.